This concept image of the Mars Explorer 1 spacecraft control deck depicts monitors and button assemblies, which will be the central nervous system of the proposed manned spacecraft. This image of Mars was received from Mars Pathfinder in 1997. This image taken by the Mars Sojourner spacecraft, which was approximately 25 feet from the Mars Pathfinder craft. This image is of the Mars Pathfinder landing bag. This bag was used for landing purposes by the Mars Pathfinder. This image, taken by the Mars Pathfinder in 1997, shows twin mountains over 20 miles away from the Mars spacecraft. This is a concept design of Deck 5 of the Mars Explorer 1 spacecraft. This deck houses all of the engines and support equipment. This image taken by the Mars Sojourner spacecraft, which was approximately 25 feet from the Mars Pathfinder, depicts Barnacle Bill, a large rock near the landing site. This early photograph, taken by the Mars Pathfinder in 1997, clearly depicts large rocks near the spacecraft. In this image, the Mars Sojourner spacecraft can be seen. This little rover had the capability of traveling nearly 200 feet from the spacecraft, which landed on Mars in 1997. This image is of the control deck of the proposed Mars Explorer 1 spacecraft. This control deck is the central nervous system of the spacecraft. It will be used during Earth launch and Mars landing, as well as control all vital functions of the spacecraft during the mission. This image shows the Mars Explorer 1 proposed spacecraft. In this image, the recreation and living quarters can be viewed. This image taken by the Mars Pathfinder spacecraft in 1997 clearly depicts a large rock next to the spacecraft. This image taken by the Mars Sojourner spacecraft shows the Mars Pathfinder mothership approximately 10 to 15 feet away. In the foreground can be seen the landing bag. This image taken by the Mars Pathfinder spacecraft in 1997 clearly depicts the Mars Sojourner ramp. This ramp was used to deploy the Mars Sojourner rover. This image taken by the Mars Pathfinder spacecraft is Mars Sunset. This image taken by the Mars Sojourner spacecraft shows a slightly hilly landscape near the spacecraft. Included in that landscape are ancient rocks. The Mars Explorer 1 spacecraft will have 3 nuke engines on board. This image is a design concept. This image, taken by the Mars Sojourner spacecraft, clearly depicts the Mars Pathfinder landing bag. This is one of the first photographs taken by the tiny Mars rover. This image taken by the Mars Sojourner spacecraft shows a valley near the landing site. This valley was thought to be a flood basin over 100 million years old. This image was taken by the Mars Sojourner spacecraft in 1997. This image is a picture of deck number 4 of the Mars Explorer 1 proposed spacecraft. In this deck can be seen oxygen and cryogenic storage tanks as well as an airlock. This picture is deck number 2 of the Mars Explorer 1 proposed spacecraft. This deck contains living areas for a 4-person crew. This image taken by the Mars Pathfinder spacecraft is a panoramic view of the rocky landing site.
The Mars Explorer 1 spacecraft has 5 decks and can support a crew of 4, up to 60 months. The spacecraft is launched on a heavy lift multi-stage rocket system. Once the second stage is spent, the Mars Explorer 1 internal liquid engines ignite, boosting the vehicle into Earth orbit. Once in orbit, the vehicle is resupplied with cryogenic propellant for the start of its 3-month trip. Once Trans-Mars insertion has been accomplished and the vehicle has escaped Earth orbit, the nuclear engines are started, propelling the spacecraft to Mars at a high rate of speed, cutting the trip in half. When the vehicle approaches Mars, the nuclear engines are shut off, and the liquid engines are once again ignited, and the vehicle aerobrakes into Mars orbit. When the landing site has been selected, the liquid engines, along with the parachute system, gently land the complete spacecraft onto the surface of Mars. Deck number 1 is the command and control center housing the engineering, navigation, communication, and central control consoles. Deck number 2 is the crew sleeping quarters and personal storage area. Deck 3 is the crew living area, consisting of the recreation compartment, the ship's galley, an exercise area, shower, and zero-G toilet. Deck 4 contains the airlock, plasma, and cryogenics storage tanks. Deck 5 houses the 4 primary liquid engines and the 3 in-flight nuclear plasma engines. Additional fuel cells, batteries, and system pumps are also located on this deck.
Deck number 4. Cryogenic storage. Deck number 4. Deck number 3. Galley. Recreation module. Exercise. Galley. Exercise. Galley. Deck number 2. Engineer. Geologist. Navigator. Commander. Engineer. Geologist. Navigator. Commander. Engineer. Deck number 2. Deck number 1. Navigation. Engineer. Commander. Deck number 1. Deck number 5. Backup batteries. Deck number 4.
NASA's current exploration plan calls for a 4-person crew consisting of a mission commander, a navigator pilot, a systems engineer, and a geologist. The unmanned vehicle that would be launched prior to the manned mission liftoff would contain mission supplies and a car, or rover, to be used for travel on the Martian surface. The exploration vehicle could carry all 4 of the crew and would run on methane fuel that would be generated from Mars' natural resources. This vehicle would have a range of up to 500 miles. This enormous driving potential would allow the astronauts the ability to explore a significant area near their landing site. The length of the crew's stay on the surface of Mars would be roughly over 1.5 years. Construction of a permanent facility on the surface would be a goal of the initial mission. Exploration and science, as well as manufacturing the return fuel, would also be essential goals. Landing at a relatively smooth site, as opposed to a mountainous or crater-filled region, would be preferred. Any manned mission to Mars, given our current technology, will be a long one. When Mars is directly on the opposite side of the Earth from the Sun, it is a condition that is called opposition. This is when Mars is at its closest approach, yet it is still 38 million miles away. At its farthest, when Mars is behind the Sun, as seen from Earth, it is called conjunction. During this stage, Mars is over 250 million miles from Earth. Unfortunately, there is no propulsion system within our technology that can push directly away from the Sun and perform the transit between Earth and Mars in a straight line when the two are in opposition. The German mathematician W. Hohmann discovered that the best time to travel from Earth to Mars occurs when the two planets are in conjunction, or at their maximum distance from each other on opposite sides of the Sun. If this path is used, the course change that is required for the spacecraft to depart and rendezvous with the planet is minimized. Deviation from such a flight plan is possible, but it gets increasingly harder to propel the spacecraft, and the cost of the mission greatly increases. If the Hohmann transfer system is not used, it may likely take at least 200 million miles along a curving arc to get from the Earth to Mars. This represents traveling 1,000 times farther than the Apollo astronauts did when they traveled to and landed on the Moon. Given our current speeds, not using the Hohmann transfer system, it would take 8 years to reach Mars. A minimum energy mission performed with one Mars-bound Hohmann transfer and one Earth-bound Hohmann transfer will be the least expensive way to complete the mission. However, this technique will require a 258-day transit each way. This will be acceptable for advanced cargo and mission setup, but not for human beings. By utilizing a combination of liquid and nuclear engines and the conjunction transfer method, current mission plans call for a 180-day travel time each way. The proposed spacecraft in front of you is designed to accommodate the 180-day travel each way, 2-year total duration mission.